Hi everybody, this is Dr. Bricker here with a video for chapter 29, which is titled Atoms and Molecules. And what we see here is, as it says here, 14,000 ton camera the size of a 4-story office building that almost completely surrounds one section of the collider and takes up to 40 million pictures every second. So this is the Large Hadron Collider, and what it's doing is investigating what atoms are actually made out of. More about that in this chapter. So to understand atoms at maybe a deeper level, we're going to use quantum physics, which we started talking about in chapter 28, to hopefully understand properties of atoms, molecules, and look at their spectra, so their emission spectra, which we talked about also in chapter 28. And this is really the fingerprints of different elements. So here you see hydrogen. So we can put gas into a tube, maybe hydrogen, helium, argon, or mercury gas into a tube, excite it by applying a voltage across it, and the electrons associated with these different elements are excited. They go to a higher energy level, drop down to a lower energy level, emit photons, and depending on what element we're talking about, we're going to see different emission spectrum. So this is what you're seeing here. This line corresponds to a certain wavelength. This is another wavelength, etc. And helium is a completely different fingerprint. So different wavelengths are emitted, different than argon, different than mercury. So we'll learn how these lines give us some hints into what atoms are actually, how they actually behave. Okay, specialized molecules in certain microscopic plankton can emit light. So these glowing waves, as you see here, are coming from the exact same idea. Okay. So the intense beams of light in a laser, as you see here, are called stimulated emissions of photons by atoms. So we won't quite get to the point where we talk about lasers, but you can take a look at this in chapter 29 when we talk about lasers. So spectroscopy is where it's all going to start in this chapter. So a spectrometer, it's a primary instrument for measuring the wavelengths of light. So we need to take light that has a whole bunch of wavelengths and break it into individual wavelengths. So this might be something like diffraction grating. So put light through a diffraction grating. Different wavelengths correspond to different angles, and we could break light into its different colors or wavelengths. This is similar to using like a prism to do this idea. Okay, so we'll take light, break it into its different wavelengths, and see what the individual wavelengths actually are. So this is just sort of a schematic here to give you an idea how this might happen. So you have a light source here. You send the light through a converging lens. The light goes through a small slit here. Another converging lens. The light ends up here on a diffraction grating, and wavelength 1 appears here. Wavelength 2 appears here, and the similar thing happens with this beam of light. Some of it ends up here, some of it ends up here. So essentially, spectroscopy just means breaking light that has multiple wavelengths into individual wavelengths, and then you could use this detector or photoplate here to figure out how much you have of a certain wavelength. So hot self-luminous objects like the sun or an old-fashioned incandescent bulb emit a continuous spectrum. So you see the whole visible spectrum, red all the way up to violet. All of those wavelengths are present. The spectrum depends on the temperature only. So in the quantum mechanical world, though, we won't see a continuous spectrum. We'll see a discrete spectrum, just like the fingerprint idea, as you see here. So hydrogen has its own fingerprint. Same thing with mercury. Same thing with neon. So you can take this a tube filled with gas, apply a voltage to it, and when you do that, some of the electrons go up in energy, drop back down in energy, emit a photon of a certain wavelength. So each of these lines, it's called the spectrum. So if you want to know what your sample is made out of, you can take a look at the spectrum. If it matches here, you've got the fingerprints of hydrogen. So every element in the periodic table has its own unique discrete atomic spectrum. I like to call it fingerprints. So each element has its own fingerprint. The fact that each element emits a unique spectrum, people didn't know why this was before. So quantum mechanics tries to explain this. In the beginning, people came up with formulas to describe this behavior, but they didn't know why. So this chapter deals with the why. Why is this happening? So what is it actually used for? Atomic spectroscopy. Well, you can analyze different samples if you don't know what it's made of. Look at the spectrum. As it says down here, monitor air pollutants, study the atmospheres of Earth and other planets to see what's actually out there. Okay. Okay, so here you see the emission spectrum. Again, what's going on is electrons in the sample are, this is for sodium it says here, electrons are gaining energy, going up, dropping back down, and when they drop back down in energy level, they emit a photon. So some of these transitions might be from like n is equal to 3 to n is equal to 2, n is equal to from 4 down to 2, 4 to 1, you know, all different kind of emission spectrums here. Now the absorption, you see some wavelengths are missing. Some are still there, like this one is still here, this one is still here, but several of these are missing. So think of this as photons are going through the sample of sodium, and say you're in the ground state and a photon comes in of a certain energy, you can grab a hold of it, go up in energy level, drop down in energy level, and just emit a photon in a random direction. So that's why it's missing here. So all of these correspond to something being in the ground state, going up and dropping back down. You rarely find an excited electron in like the n is equal to 2, 3, 4 state. So that's why you don't see the lines here. So these missing ones correspond to starting in the ground state and then going up and emitting a photon in a random direction, so you're not measuring it here. The other ones would be something like if something was in the n is equal to 2 state, grabbing a photon going up and dropping back down, but you rarely find them in that state, so you don't see the absorption pattern here. So that's a difference. Okay, so this is what it might look like, just kind of a generic schematic of it. White light, that means it has all the wavelengths, go through a converging lens. The white light then goes through the sample filled with gas, like it could be the mercury from the last one. And the sample here could grab onto some of the photons, go up in energy level, and then drop back down, emit a photon in a random direction, so that wavelength would be missing from the absorption spectrum. Okay? So similar idea, it's just you're sending the white light through a sample and you're in a sense weeding out some of the wavelengths. You're weeding them out in the sense that they don't end up here, they go in random directions and don't end up here. Okay. So 1885, Swiss school teacher Johann Balmer, maybe you've heard of the Balmer series from chemistry, determined the wavelengths of spectral lines of hydrogen. So this was just for hydrogen. It turns out a lot of the talk in this chapter is about hydrogen because it's the simplest of the elements, which only has 4 lines in the visible spectrum. So it emits different photons, but the ones that you can actually see with your eyes, there's 4 lines in the spectrum. And he didn't know why this was. He just knew this formula worked. So the wavelength of the emitted photon, 91.1 nanometers divided by 1 over 2 squared minus 1 over n squared. And here n is 345. So the emission spectrum, you can plug in 3, 4, 5, etc., and come up with the Balmer series. Later, experimental evidence showed that Balmer's results could be generalized to this formula, 91.1 nanometers, 1 over m squared minus 1 over n squared. And here, so m can be 1, 2, or 3. It's just an integer. N can be any integer greater than m. Okay, so you're going from a higher state to a lower state. N is bigger than m. Okay, so you're dropping down an energy level. N is bigger than m. So when you put the numbers in here, you have what's known as the Balmer formula. Okay, good. And these are the wavelengths of visible light in the hydrogen spectrum then. So this is the fingerprint of hydrogen. That's what you can see with your eyes, these 4 different wavelengths. And they correspond to different colors. Okay, so the Balmer formula accurately describes every wavelength in the spectrum. It's just an empirical formula. It's not based on any science. He was just able to mathematically come up with this formula. It took another 30 years or so to actually understand the physics behind this, and this is quantum mechanics. Okay, so a little bit about atoms. Uh, 1897, J.J. Thomson discovered the first subatomic particle, the electron. So this is relatively recent if you think about it, 1897. The mass of the electron is much smaller than the mass of the whole atom, so he thought the atom consisted of negatively charged electrons embedded in this more massive positive cloud. To us, it seems silly to think about it like that, but this is what they thought. Here's the actual atom. In the atom, we have these electrons. It's all sort of mixed together, something called the raisin cake model. And the size of this thing is something like 10 to the minus 10th meters. Okay, again, for us, this is so foreign to us because we've learned different. We learned the electrons orbit a nucleus. Here they're sort of saying it was all together. So some experimentation had to be done to prove this right or wrong. It turns out it was not correct. Rutherford, former student of Thomson, discovered that a uranium crystal can emit two different rays, beta rays and alpha rays. It turns out that beta rays are just they're just electrons that are traveling at high speed, and alpha rays turned out to be helium nuclei, actually. Alpha rays, now called alpha particles, consist of helium nuclei. Okay, good. And here's the mass of that. If it's helium, it's got 2 neutrons and 2 protons, so this is the total mass. Emitted at high speed from the sample. So this is uranium crystal that's decaying. Some of the decay products are beta rays, which again, high-speed electrons, and alpha rays. These were the first observations that atoms have an inner structure and that some atoms were not stable and could spit out various charged particles. In other words, they discovered radioactive particles. So uranium decays. Some of the decay products are alpha rays, or in other words, helium nuclei. Some are electrons. Okay, so atoms aren't completely stable, in other words. So Rutherford then set up an experiment to probe the inside of an atom. He shot high-speed alpha particles through a thin gold foil. Okay, so sort of probing the gold foil with alpha particles. So if you have a uranium sample, it's decaying. Decay products are going to go through the gold. So the idea here is if the atom structure was described by Thomson's raisin cake model, then the forces exerted on the alpha particle would sort of balance out as the helium went through there, and it would just go right through it, deflect a little bit. I think there's a better picture on the next slide, maybe the one after this. Radioactive sample, some lead blocks just for safety reasons, and the helium nuclei would hit the gold and then just be slightly deflected. Because, you know, the nucleus isn't solid like we think of it now. It's sort of all spread out. Kind of like this. If this is Thomson's model, the alpha particle would be, you know, repulsed by the positive charge, attracted to the negative, on average just kind of sort of make its way right through, and nothing would bounce back at you if this were true. It turns out this isn't what happened. Some of the alpha particles went right towards the nucleus and basically bounced right back at them. So if the atom has a concentrated positive nucleus, some alpha particles will be able to come very close to the nucleus and feel a very strong repulsive force and then bounce back at large angles, or maybe even bounce straight back at the source. Discovery of a large-scale scattering of alpha particles. In other words, they bounced back. They didn't make it right through. They hit the nucleus, some of them did, and bounced right back. So this is sort of a proof that the atom is got the mass concentrated in the nucleus. Most of the space is actually empty, but the nucleus is where most of the mass is located. And then we have the electrons orbiting around the nucleus. Okay, a few things about using this nuclear model. And this is the model that we take for granted nowadays, probably since like 4th grade or something. The atomic number of an element indicates its position in the periodic table, and this is simply the number of protons. So the number of protons determines what it is. So say oxygen, for example, atomic number 8, that means it has 8 protons. Another way of saying it is if it has 8 protons, it's oxygen. Carbon has 6 protons. So another way of saying that is it has 6 protons, it's carbon. So the number of protons determines what the element actually is. So atomic number represented by Z here. So hydrogen, Z is 1, helium, Z is 2. Now if it were neutral, helium would have 2 electrons, and 2 protons, 2 electrons. That would be neutral. If hydrogen's neutral, it has 1 electron. So 1 positive charge, 1 negative, or sorry, 1 positive charge from the proton, 1 negative charge from the electron. Okay, I mean, if you look at the whole periodic table, that's how it's arranged. Okay, so orbiting electrons are very light, so a photon or a rapidly moving particle, like another electron, for example, can knock an electron away, creating a positive ion. You could actually take like a piece of plastic and rub it with fur and remove or add electrons that way, so you can knock them out. They're sometimes loosely held. Sometimes they're not. They're strongly held, like a noble gas, but here we're just talking about things that you could easily remove. So this is actually neutral. 3 positive charges, 3 protons, 3 electrons. That one's neutral. Here somehow an electron has been knocked off, leaving this with a negative, with a positive charge, because 3 protons, 2 electrons, net positive charge. Here, same idea. This is where 2 electrons have been removed. Okay, and again, that's what we're used to thinking about atoms being. So positive charge of the nucleus associated with a particle called a proton. As we know, protons charge 1.6 to the minus 19th coulombs. In terms of mass, the proton's way more massive than an electron, 1,800 times more massive. Okay, so electrons are more easily transferred than protons because protons are tightly bound to the nucleus. And we saw this when we talked about current and charging something up, current running through metals. Electrons are the charge carriers because they're easily removed. The protons are bound together in the nucleus. It's hard to break the nucleus apart. Nuclear forces hold them together. So scientists realized that the sum of the masses of the protons and electrons did not add up to the total mass of the atom, so something was still missing. And this is relatively recent, right? 1932, the third atomic particle, the neutron, was actually discovered. So a neutron essentially the same mass as a proton, but no charge. It resides in the nucleus with the protons. And neutrons help to kind of glue the whole nucleus together with something called nuclear forces. Okay, so similar mass, almost the same mass as a proton, but no charges. So protons determine what the element is, and different isotopes of elements have different numbers of neutrons, as we'll see in just a minute. So a nucleus contains Z protons plus N neutrons. So the mass number, it's the number of protons plus the number of neutrons. So, for example, carbon, regular carbon that we're used to, has 6 protons and 6 neutrons, so carbon 12. There's also a version of carbon that has 8 neutrons and 6 protons, so carbon 14. That's radioactive carbon. That actually decays. There's carbon 13. Again, carbon, so it has 6 protons, but carbon 13 would have 7 neutrons. Both of those, carbon 13 and 14, are not stable. They eventually decay. You actually have some carbon 14 in your body right now that's decaying. Okay? Proton and neutron masses are one atomic mass unit. When I was a kid, we had to write out 1 AMU. Here you could just write out 1 U. So there's been some progress in that, I guess. But this stands for 1 atomic mass unit. In terms of SI units, it would be 1.66 to the minus 27th kilograms. Okay, and this is sort of a visualization of what the nucleus might look like. Okay, very good. So think about the periodic table. If you see carbon 12, it has 12 AMUs, and each of those is this many kilograms. Okay, there is a range of neutron numbers that can form a nucleus with Z protons, and these are the isotopes I was talking about. So for example, you could have like carbon 12, which is stable carbon, carbon 13, carbon 14. There's isotopes of oxygen. We've got regular 16 oxygen. There's also 15, 17, those other ones are not stable, they decay. Okay, so the notation for isotopes is A to the Z. So, sorry, A here, Z here. A is the mass number. What is the mass number again? It's the number of protons plus neutrons. So here's helium-3. Here's helium-4. Helium-4, it's helium, so it has 2 protons, but also 2 neutrons. Here's helium-3, and helium, because it's helium, 2 protons, and if you got 3 here, you must have 1 neutron. So most helium is this version, 99.999%, but a smaller amount comes in helium-3. Okay, good. So Bohr's model of atomic quantization. So a lot of this stuff that you're about to see in the next couple of sections deals with looking at the hydrogen molecule classically in terms of things that we really did in Physics 220, and then applying this quantization idea to classical mechanics. There was no good reason to really do it. People who worked on this, like Bohr, for example, they relied on classical mechanics, and then they tried to apply this quantization idea to hydrogen, for example. It turns out they were right. They didn't really have any reason to do it. It was almost lucky that they did that, but it turns out they were right. Okay, so according to Maxwell's theory of electricity and magnetism, electrons orbiting the nucleus, they're orbiting it, so when you're going in a circle, you're accelerating. If you did this, you should give off energy. So anything that's accelerating will give off an electromagnetic wave. We would see a decay in energy, so here's an electron giving off energy, slowly ending up at the center. But this is not what happens. Electrons don't end up in the nucleus. They continue to orbit. So there was something more that it was clear here, as it says, Rutherford model was not a complete model. We had to do more with it. So Niels Bohr, 1913. Again, this is relatively recent stuff in terms of physics. Like Newton was in the 1600s. This is the 1900s. Okay. So anyway, Bohr proposed a new model which added quantization to Rutherford's model. So we're taking classical mechanics and trying to add this idea of quantization, where you could only have certain allowed energy levels. And it turns out certain allowed angular momentum, certain allowed radii when electrons go around the nucleus. And this is called the Bohr model of an atom. Okay, so according to Bohr, the electrons in an atom can exist only in certain allowed orbits, and a particular arrangement of electrons is called a stationary state. So these electrons just can't be anywhere. They can only be allowed in certain radii. Again, there was no reason to try to do this. They just thought, oh, things seem like they're quantized. Let's go with this and see where it leads. So then each of these stationary states has a certain energy associated with it. So here's the ground level, n is equal to 1. These are excited states. Okay, and you can see here both electrons in this schematic are both in the lowest state here. One of them has gone up to a higher level here, even a higher level. So each stationary state has a discrete, so only one allowed, well-defined energy, and the energy level diagram is associated with that. Okay, and we could number these by something called quantum numbers. So n is equal to 1 means ground state. This is a excited state. This is even a more excited state. How do they get these excited states? Grab a hold of a photon, go up in energy. When they transition back down, they would emit a photon. Okay, well, as it says here. So a photon emission means you had an electron in a higher energy level. It drops down to a lower energy level and gives off a photon. Okay, how does that happen to begin with? A photon comes in. If the photon has enough energy to go from one level to the next, the electron can grab a hold of it, go up in energy. So really the absorption would happen first, and then the emission would happen secondly. Okay, so these are called quantum jumps. Quantum because there's nothing in between here. You can go from here to here. You can't end up somewhere in the middle. Okay. If you go into the tech building on the Westville campus, you can go up the steps. So you're on one step, you're on another step, you're at another step. That's sort of a quantized way of looking at it. Or you could take the ramp and you could be anywhere on the ramp. That's the non-quantized real world, macro world that we live in way of looking at it. But in the quantum mechanical world, you can only be on certain steps. Okay. Atoms can also move from lower energy states to a higher energy state by absorbing energy in a collision with an electron. So it doesn't have to be a photon. An electron can come in, collide, and we can go up in a higher energy level that way, drop back down, and same thing, emit a photon. So this is something called collisional excitation. Okay, so this is very abstract. You can't see this with your eyes, but it turns out everything that you're seeing here is true. It almost makes it more magical, though. Okay. Okay, so we've got a couple of implications of Bohr's model then. So matter is stable, it says up here. So matter is stable. So once you're in the ground state, there's no lower state than that. You can go up in energy, but you can't go any lower than the ground state. So in that sense, the matter is stable. And atoms emit and absorb only in a discrete spectrum. So there's only certain lines, like for example, the emission spectrum of hydrogen. There's only a discrete spectrum. You see individual lines at certain wavelengths. There's nothing in between there. So when an atom jumps from the initial state of like E initial to the final state EF, F just means final, conservation of energy requires that it emits or absorbs a photon of the difference in energy. So if you're in the ground state, you want to go up to the next state, you have to absorb a photon that has that difference in energy between those two states. Now, if you want to know the frequency or the wavelength of the photon, we can use this equation. Energy of the photon is equal to HF. So the difference in energy to go from one state to the next, either emission spectrum or absorption spectrum, has to be H times F. Good. So the difference in energy, H times F. H is Planck's constant that we saw before, or Hc over the wavelength. And if you want H times C, we used this little shortcut before, 1240 eV nanometers. And we'll get some practice using that. We already did in chapter 28, but we'll look at it again. Okay, good. So only certain wavelengths are permitted. And emission spectrum can also be produced by collisions with and kick up to a higher energy level and then drop back down. Okay, same idea. The amount of the frequency is related to the difference in energy levels. Again, we'll get some practice with that. Absorption wavelengths are a subset of the wavelengths in the emission spectrum. And I'll read this because maybe they say it a little better than I did. Recall that all the lines in the absorption spectrum are also seen in emission, but many emission lines are not seen in absorption. According to Bohr's model, most atoms, most of the time, are in their lowest energy state. Thus, the absorption spectrum consists of only those transitions from 1 to 2, 1 to 3. 2 to 3 are very, very rare, as I said before, because you're not going to find the atom in the 2 state to go up to the 3 state and remove that line, so that you just don't see it in the absorption spectrum. Those are all ground state, or in other words, n is equal to 1 situations. Okay, so again, think back to what the absorption spectrum looks like compared to the emission spectrum. And then each element has its own unique spectrum, its own fingerprint. Really, that's the fingerprint of an atom, okay, the emission spectrum. Here's an example. An atom has stationary states 0 eV, 2 eV, and 5 eV. What wavelengths are observed in the absorption spectrum and in the emission spectrum? Okay, let's see what we have here. So here's what the energy level diagram would be. Absorption transitions must start with n is equal to 1. So you're always going from 1 to 2 or from 1 up to 3. This is the spectrum where you just see certain ones missing. The emission spectrum, though, you can go from 5 all the way down to ground. So 5 eV down to ground. That's this one. Or if you're in n is equal to 2, you can go from 2 down to ground, or you can go from 3 to 2. So notice that there's 3 lines here, and there's 2 lines in the first one. Okay, So it's the difference in energy that we're concerned about. So, like for example, from 5 to 0, the difference in energy would be 5 eV. From 5 down to 2, the difference is 3 eV. From 2 down to 0, the difference is 2 eV. Okay, and we can calculate the wavelength associated with that. Okay, kind of a synopsis of what I just said here in this slide. Okay, so looks like here we're calculating the absorption spectrum, as it says here, from 1 to 2 and from 1 to 3. So from 1 to 3, we could use this equation. Difference in energy is equal to H times F. So the difference in energy divided by H is equal to F. That's what's being used here. The frequency is the difference in energy, 5 eV, divided by Planck's constant. You put in the numbers and you get 1.2 times 10 to the 15 hertz. If you want to convert that to a wavelength, how do you do that again? Frequency times wavelength. So the wavelength is the speed of light divided by the frequency. And then you can convert it to a wavelength if you want to. Don't forget the speed of light is this, 3 times 10 to the 8th meters per second. Okay. Good. And same idea from going from 1 to 2. The difference in energy is 2 eV divided by Planck's constant. You get the frequency. And then if you want, you could turn that into wavelength from that formula. Okay. Very good. Be careful with the units. We saw two different, not versions, but we've seen H in two different sets of units, the EV version and the joules version. Okay, good. So emission spectrum, it's the same idea. You're going from 2 to 1, from 3 to 1, but then you can also go from 3 to 2. And it's the same idea. We'll just figure out the difference in energy, and the same way that you did it before, you can calculate the frequency and then the wavelength. Here's an easy way of doing it. Difference in energy, HC over the wavelength. So the wavelength then is HC divided by the difference in energy. So let me just pick one. 1240 EV nanometers, and then let's look at the one from 3 to 2 because the numbers are easy. The difference in energy is 3 EV. Now if you plug 3 EV in here, that's the difference in energy. You get the wavelength. The EV part cancels out. We're left with nanometers. So it looks like 4, 1, 0 or so would be this one. Yeah, okay, good. All right, excellent. So the Bohr hydrogen model then. So this figure shows sort of a classical way of thinking about it. Here's an electron orbiting the nucleus. There has to be a force towards the center. This is positive, the electron is negative, so there's an electric force towards the center. And we saw this from the beginning of the semester, really. We looked at it like this. K, Q1, Q2 divided by R squared. That's what this formula really is. Don't forget you can write K as 1 over 4 pi epsilon naught. Now the Q1 and the Q2, those are both the fundamental charge because one's a proton and one's an electron. And then R is the distance between them. So that's the force that's directed towards the center. So we know from before, this is going back to physics 220, F is equal to ma, special kind of a towards the center, called the radial acceleration. This would be mv squared over r. And then the force that's actually towards the center is the electric force. So 1 over 4 pi epsilon naught charge squared divided by r squared. And then a few things will end up canceling out. And you could do a little bit of rearranging of that. That's where this formula is actually coming from. If you take a look at this and you solve for v. Okay, this r cancels with one of those r's. You got to divide both sides by m. So if you do that to this formula, that's where this is actually coming from. That's the speed of the electron. Now we can apply the quantization idea. So if you treat the electron as a de Broglie wave, the particle will set up a standing wave, just like we saw before, just like the particle in the box. So if there are waves traveling in both directions, and if the round trip is an integer number of wavelengths, right? If this is going along and it has a certain wavelength, it's got to be a complete wave to actually fill the orbit. So if you go around here, if it has a wavelength, the wave actually has to fit around there. Okay, we could apply this condition that the circumference of the circle, 2 pi r, has to be a multiple of the wavelength. So this is the circumference of the circle. It has to be, that's not the speed of light. This is the circumference of a circle. Has to be a multiple of the wavelength to actually fit the wavelength in this orbit. So we're quantizing what's going on here. So we've got the classical idea here, and I even mentioned physics 220, but now we have this idea. This will tell us what R has to be. Okay, so let's put those ideas together. Okay, so put them together with the de Broglie wavelength idea. So wavelength was h over p. P's the momentum, so we can put in mv for the momentum. So if you take this for the wavelength, plug it into what you had on the previous slide. This is what was on the previous slide. N times the wavelength. Take this, plug it in for the wavelength. 2 pi r then has to be n h over v, and then solve for v. You get this. This has to be the same v that we looked at classically. This is applying quantum mechanics to this whole situation. So the electron can't have just any speed. You can only have values dictated by this. So really it's when n is equal to 1, it would be h 2 pi m r. When n is 2, it's h 2 pi m r, just like you see here. So there's only certain discrete speeds allowed. To make our lives a little bit easier, and this is really getting into quantum mechanics now, this is called h bar. So maybe you don't want to write 2 pi all the time. That's why physicists came up with this. They got tired of writing 2 pi. H bar, that's how it's pronounced, is h divided by 2 pi. So instead of h, Planck's constant we had before, this is called h bar. If you put the values in for 2 and pi, you get this for h bar. Okay, and then this cleans up the velocity a little bit, or I should say speed. Cleans up the speed a little bit. So the speed has to be multiples of h over mr, right? This is n, and n is just 1, 2, 3. So you have 1 h bar over mr, or 2 h bar over mr. Those are the allowed speeds. Okay, good. So in the beginning of this discussion, we looked at the particle classically behaving as an actual particle, and that's this part comes from. And when you analyze it behaving like a wave, v squared has to be this. Those v's have to be the same thing. So you can set those equal to each other and solve for this radius. So these are this is the allowed radius of an electron orbiting a hydrogen atom. It's n squared 4 pi epsilon naught h bar squared over me squared. Absolutely no intuition. You cannot come up with this formula off the top of your head. This is Bohr looking at this classically and then applying this quantization idea, setting those ideas equal to each other and coming up with this. So maybe you've heard of the Bohr radius before from chemistry. So this is the Bohr radius here. So we can group together constants and define the Bohr radius as this, right? This is an electron, so we know the mass of an electron, we know the charge, we know what h bar is, we know what epsilon naught is. Put that all together, multiply all these things out, and you get the Bohr radius as 5.29 to the minus 11th meters, so 0.0529 nanometers. And again, maybe from chemistry you've come across this number before. Okay. All right, very good. So then the allowed orbits are just multiples of the Bohr radius. So when n is equal to 1, you just get the Bohr radius back when you plug 1 in there. When you get the n is equal to 2 level, plug that in, the orbit would be 4 times the Bohr radius. When n is equal to 3, plug 3 in here, you get 9 times. the Bohr radius. So hydrogen atom can only exist if the radius of the electron's orbit is one of the values given by this equation. So it's quantized. You can only have certain orbits governed by this equation. A mixture of both classical mechanics, treating the electron as an actual particle, and also treating the electron as a wave. Mixing both of those ideas together, you get this. So it works with the radius. It's going to work with different energy levels, different angular momentum. All that's going to work out. Okay. Okay, let's do this, and then I'll make another video for the second part of this. So the total amount of energy we have is kinetic energy plus potential energy. So from Physics 220, 1/2 mv squared, that's the kinetic energy. From what we've done in this class, this is the electrical potential energy between charges. We can group this together a little bit, or not really group it together, but plug in what these charges actually are. It's the fundamental charge E. So you can plug that in. That's where the negative sign comes from then. We saw before what V has to be, so you could take this for V, and we're going to end up putting it in here. So this is a little derivation. We'll get the result. We'll be able to use the results of that. Okay, so 1/2 mv squared, we're going to plug this in for V. This part's going to stay the same. You can plug in the Bohr radius here to get this value then. So it's messy. You put it all together, things clean up nicely, and the energy levels of hydrogen turn out to be equal to this. And we can actually plug in the value of E, epsilon naught, Bohr radius, and come up with this. So maybe you've seen this from chemistry too. So the ground state energy, 13.6 eV. That's what it's defined to be there. So the energy levels then minus E1 over n squared. So when n is 1, you get minus 13.6 eV. E2, you can plug that in. You would take 13.6 divided by 2 squared, which would be 4, etc. Okay, good. So again, maybe you've seen that from chemistry, the ground state energy of hydrogen. So if you want to remove an electron from hydrogen, you've got to supply 13.6 eV of energy. Okay, so here's a nice table of some of these values. This is the Bohr radius here. Here's the speed associated with that. Here's the energy. That's what it is. That's the only thing that it's allowed to be. When n is equal to 2, you get this for the orbital radius, you get this for the speed, and you get this for the energy, etc. And here's a nice picture that goes along with it. So these are the 4 stationary states or allowed orbits in the Bohr model of hydrogen. So this is complicated enough. Imagine when you start going up to things like uranium and you got all these protons, all these electrons. It's doable, but we're going to stick with hydrogen. Okay, so we'll start with this for part 2 of chapter 29. Okay, talk to you later. Bye-bye.